Swayam Prabha. Digital India. Educated India.
Sir, you are live now. You can start your session.
Okay, thank you. Very good evening and welcome to this second live session. I'll share my screen. So now we can see the course title and you can see the date. We are meeting on 28th of March 2024 for the second live session for the NPTEL course Fundamentals of Theoretical and Experimental Aerodynamics. I am Professor Arnav Roy from Department of Aerospace Engineering, IIT Kharagpur, offering the course. And I am very ably supported by my scholars, PA students, Mr. Arpit Mishra, who is an ex-scholar, and Mr. Arjun Garva, current scholar of Cryogenic Engineering Center of IIT Kharagpur. The course title, as you all know, is NOC 24AE04. It's a rerun course being offered from Jan to April 2024. I'm extremely thankful for the very active participation of the students, the scholars who are part of this course. And I'm also very much indebted to the NPTEL staff members at IIT Kharagpur as well as at IIT Madras who are coordinating this entire activity from behind the scene and have been of enormous help to us in order to make it successful. And we are extremely grateful to the Ministry of Education, Government of India for providing us the platform to offer such courses and make it useful for the students. We begin by looking at some of the queries that we have been receiving from time to time on the discussion forum. One of those questions is posted by Om Acharya related to assignment number 5, question number 11. And there he's asking a question regarding finite wing theory. Shouldn't the question statement contain the value of A naught be given to use in the formula for A? That is the query that he has. And this is basically the question where you have been asked regarding finite wing with a general planform geometry with an aspect ratio of 9 and taper ratio of 0.5. And you have to determine the induced drag coefficient at an angle of attack of 4 degrees. And you are asked to assume that the wing has a thin symmetric airfoil section. And the values of tau and delta are 0.07. So having said that, we can go to the solution. We take note of the aspect ratio. As you know, as aspect ratio becomes larger and larger, and typically as it tends towards infinity, the characteristics of the finite wing tend towards the characteristics of the infinite wing or the airfoil. Here you have been given the tip to root ratio and the angle of attack. And since you are dealing with a thin airfoil, therefore the lift curve slope is 2 pi. And the zero lift angle of attack is 0 degree because it's a symmetric one. So this is something that you would be expected to know. And therefore, even if it is not given in the question, you are expected to plug in this value and then solve the problem. Coming to the drag coefficient, we know the induced drag coefficient is given by this expression. You can also introduce the E parameter in the denominator and solve it instead of having the 1 plus delta in the numerator. And as far as the lift coefficient of the finite wing is concerned, it is A times alpha, where A is the lift curve slope for the finite wing, where you have to plug in the lift curve slope of the infinite wing as well as the aspect ratio and the tau values. For the given problem, we just plug in those values and we get this figure of 0.0886 per degree. As you may recall that this is about 0.11 for the thin airfoil. And when it comes to the CL, you get a value of 0.354 approximately. When it comes to calculating the CDI, which is dependent on the CL, once you plug in that value, you get an induced drag coefficient of 0.0047. So that's how we work out the problem. And back to this detail, which you really inquired about. So that is something that will be considered to be a known to you. It's a knowledge base which you should be carrying with you while solving such problems. And just in case you need to brush up these fundamentals, you need to go back to lecture number 29. All these are available now, and you can just get into that lecture and listen to the relevant portions so that you are able to recall. And we have just put a small figure out here to show that how the infinite wing and finite wing lift curve slows vary. And as you may recall that when it is the lowercase CL, then we refer to the infinite wing, while the uppercase CL with the capital refers to a finite wing. So there are nomenclature issues here which we have to keep track of. The slope issues also which we have to keep track of. Also the zero lift angle of attack which needs to be kept in mind. And that has to do with symmetry or asymmetry of the section. When it is an asymmetric one, then you find that this angle happens to be a value other than zero, usually a negative angle. And then when you plug the information in terms of the slope of the lift curve, this is how it works for the infinite wing, while as far as the finite wing is concerned, we can show that it comes out to be this. And then this is the formula which we actually ended up using while solving that problem. And you may recall in the same lecture, we had solved another problem where the figures were slightly different, aspect ratio or taper ratio, etc. So if you look at this problem solution, again, we are considering this A0 value as a known fact. So with that, we move on to the next query from Tushar. So he wants to know that how is the grading procedure affected if I'm not able to submit any assignment for the specified week? Is it compulsory to attend each one of it, or does the best 8 out of 12 criteria still holds good? Now, without going into any kind of a speculation here, what I would like to advise you is that if you go into the NPTEL forum, you will find that these are the requirements that have been stated by the NPTEL team in terms of criterion to get a certificate. So if you read through that, again, the same facts are emphasized. And then it's implied that if you are attempting all the 12, then your chances of scoring better in the 8 best that are picked rises to that extent. And that is what you are recommended to do. And if you just attempt 8, then there would be no provision for, disregarding 1 or 2 assignments where you may not have performed all that well, so that your average just improves a bit. So attempting 12 assignments, all 12 is what is recommended. All right, so the rest of the rules, of course, follow. And as is stated here, very importantly, that you will be eligible for a certificate only if average assignment score happens to be greater than equal to 10 out of 25. 25 is coming from the fact that they have 25% weightage on the assignments. And then the exam score should be greater than equal to 30 on 75, where the exam score is given 75% weightage. And if one of the 2 criteria is not met, you will not get the certificate, even if the final score happens to be greater than equal to 40. So this part of the facts and figures is very, very important. And I'm sure with the effort that you are putting in, you should be able to do very well and definitely cross this and score much better than this. Moving on to the next point, which Om Acharya has raised, is a doubt in assignment 6. And he has talked about which phenomena occurs due to adverse pressure gradient across incident shock in shock wave boundary layer interaction scenario. So whether all options are correct, that's the statement that has been made, for which I think it will be good that we have a relook at the entire phenomena once again. This is a very important sketch that we are looking at. We may recall that a supersonic flow is approaching the flat plate and moving past this flat surface from the left towards the right, and you have an incident shock coming and impinging on that flat plate, which is formed by some kind of a surface which acts like a shock generator. And the moment it impinges on the boundary layer, it can of course go only up to the sonic line and not below that, because below this line, if you start moving towards the wall, the flow has become subsonic and therefore the shock cannot exist there. So this incident shock goes right up to the sonic line. And then the moment that happens, because of the adverse pressure gradient that is felt by the boundary layer, and because within the subsonic regime, which you have below the sonic line, the information of the adverse pressure gradient can move both upstream as well as downstream. You immediately see the separation bubble cropping up because the upstream flow becomes aware of the adverse pressure gradient or its presence, and therefore the separation shock is formed. Separation shock interacts with the incident shock, and there comes your transmitted shocks. So that is what is mentioned here, that you would end up seeing transmitted shocks, and that's precisely why it happens. And then the transmitted shock penetrates the separated viscous flow up to the sonic line and is reflected as a Prandtl-Meyer expansion fan, because there is a near constant pressure level in the bubble. So within the separation bubble, the pressure nearly remains constant, and it's like a shock impinging on a constant pressure boundary. It reflects back as an expansion fan. So the rules of the game are mentioned here, that if you have a shock wave incident on a solid boundary, then it reflects like a shock wave. If it is incident on a constant pressure boundary, it reflects as an opposite kind, that means an expansion wave. And this causes even a deflection of the shear layer. So what we mean by the shear layer is this layer across which there is a dramatic velocity change in the tangential direction. And then because of the deflection that that interaction brings about, it eventually reattaches. And as that happens, even compression waves are emanated from the reattachment location, and therefore you have a reattachment shock as well, what we can see over here. So there are a lot of flow features which we can see here, and now based on that, we can figure out how to answer such questions. Moving on to the next query, which is from Anthony. The doubt is in lecture 46. When substituting the del u del t and del 2u del y square terms in the governing equation, why aren't the leading error terms taken for dou u dou t, and similarly the error term corresponding to this? So let's try to understand what the question is about. We'll look at the slide which we had used in the lecture. So we are talking about a parabolic partial differential equation, which is basically a diffusion problem. So here you have momentum diffusion happening in the Stokes' first problem. You have a moving wall on top and a stagnant Newtonian fluid within the gap. And then here you see how the momentum diffuses into the gap. And then at large times, after the starting of movement of the upper plate, you see that you have a perfect linear profile, which is essentially the Couette flow solution. And kinematic viscosity or momentum diffusivity is responsible for transporting the momentum to the different levels, right through the thickness of the fluid layer. And the question is essentially related to how we work out this the derivative expression and how we show the truncation error terms. So we essentially do a kind of Taylor series expansion. We use the time coordinate for that. And then we have the functional value, the derivative, first order derivative, second order derivative terms multiplied by the delta t raised to the power of n by n factorial. And then when you rearrange the terms, you get an expression for del u del t at that point xt. And this is basically a kind of forward differential expression in terms of time. And then you find that, of course, you are left with terms like this. And what we mean over here is that these terms, which are essentially, there are infinite of them, these are essentially going to be neglected. So what we say is that these are truncation error terms, truncation in the sense that we are going to truncate off all those remaining terms from the second order derivative onwards, and they would essentially be neglected when you make use of the derivative expression which you are approximately writing through this finite difference equation. So you are basically, what you are doing is you are approximately representing this first order derivative by this algebraic expression, and you are neglecting all these terms which we call as the higher order terms, and that is what we mean by truncation error. All right, so you do not retain them really, you drop them out. Similar strategies are used for devising expression for the second order derivative, for example. So when you uh, formulate the equation for second order derivative, you will find that we would have done a similar exercise there too. Okay, so based on that, what you end up having is an algebraic form to represent the partial differential equation. So that's of course an approximate form, but that's what we use for the numerical solution finally. And in those approximations, terms like these are dropped out. So that was the next question. And these are the important questions that we found in the discussion forum. We'll try to spend a few minutes now on trying to quickly recapitulate the contents that we have tried covering in the course. We recall that week 1 to week 6 of the course were basically covering theoretical aspects of aerodynamics. For example, in week 1, we tried to look at the 3 major components or approaches in modern aerodynamic studies. So we said that it's theoretical, which could be analytical or semi-analytical, experimental, as well as numerical approaches, which form modern day CFD, the modern day studies of aerodynamics. And the computational aspect of aerodynamics is called as the computational fluid dynamics or computational aerodynamics. And these different approaches are often meant to complement each other and validate each other while we study a particular problem, particular aerodynamic problem. And then we moved on to the concept of standard atmosphere, where we looked at geometric, absolute, and geopotential altitudes. We also looked at the temperature distribution as it occurs through the standard atmosphere. There are several isothermal and gradient regions that we looked at, spanning right up to about 100 kilometers altitude from the ground level. And then we looked at equation of state, how we use it to obtain pressure and density variation through those different isothermal and gradient regions. Then we introduced important concepts related to aerodynamic flows like pressure, density, temperature, flow velocity, skin friction. And then in the subsequent weeks, we developed more concepts and tried to mature those ideas. We also looked at the genesis of weight, lift, how the role of flow turning is there for lift generation on lifting surfaces like airfoils and wings. We looked at thrust. We saw the thrust equation for air breathing engine. And then we looked at the drag forces, different components of drags like skin friction drag, pressure drag, induced drag, wave drag, and their balance in steady level flight. We also discussed gradually about where these different kinds of drags may exist. You may recall that induced drag is something that would not exist for a two-dimensional body like airfoil. It would exist for a finite wing, while wave drag is something that we'll not see at low speeds. It will happen in supersonic conditions and things like that. When we make a kind of hypothesis that the flow is inviscid, then there's no question of accounting for skin friction drag. So through these subtleties, you try to understand that where each one of those components fit in. Integration of pressure and shear stress to obtain forces and moments on an airfoil, relation between normal force, axial force, lift force, drag force, and also how they are connected through the angle of attack. So important relations that we can see over here, lift expressed in the form of as a function of normal force, axial force, and alpha. Similarly, drag. And you can also invert these relations and express normal force and axial force in terms of lift, drag, and angle of attack. So these are things that you should become very familiar with. Then came non-dimensional coefficients for different parameters like pressure, skin friction, force, moments, and the nomenclature, the 2D and 3D body nomenclatures. And then we also familiarized ourselves with aircraft external shapes and surfaces. You may recall having seen diagrams like this where we showed different control surfaces on an aircraft and so on. This is a diagram where we talked about steady level for flight and how the forces balance each other. These are the different components of forces and moments which can act on an aircraft and so on. And this is a very classical picture of the different forces which act on an airfoil and the angle of attack. Moving on to the week 2, we looked at concepts like Eulerian and Lagrangian perspectives of flow. The Eulerian approach is a control volume approach. Lagrangian approach concerns tracking individual fluid particles and looking at their trajectories in the form of streamlines, path lines, streak lines, and so on. Then we looked at fluid kinematics, angular velocity, curl of velocity vector, vorticity, strain of a fluid element, rotational, irrotational flow, their classifications, circulation and vorticity, velocity potential, and so on. We revised important mathematical concepts like gradient, divergence, and then different kinds of integrals like line, surface, and volume integrals on open as well as closed surfaces. We learned about important theorems like Stokes theorem, divergence theorem, gradient theorem, which are extremely important in aerodynamic studies. And then we moved into the conservation equations of mass, momentum, energy, both in integral and differential forms. So very important conceptual entities were introduced in this week, and then we moved on to inviscid and viscous flows, potential flow, boundary layer flow, then compressible and incompressible flow, laminar and turbulent flow. We learned how to segregate them, how to differentiate them, how to define them, and so on. We understood that fluid friction due to viscosity is what is the dominant feature in a viscous flow, slip and no slip conditions in the context of inviscid equations and viscous equations, pressure gradients in the sense of favorable, adverse, and neutral, how they may influence a viscous flow and thereby cause attached or separated flows. Following a fluid particle, we discussed about substantial derivative, and we talked about fluid element acceleration. We understood the significance of Reynolds number, and we saw it in Navier-Stokes equation. Euler equation, of course, does not contain any viscous terms. So does Bernoulli's equation, and we also learned that Bernoulli's equation can be derived by starting from Euler equation and applying certain further assumptions. Compressibility of a fluid medium was taught from fundamentals. We learned about a very important instrument, the pitot static tube. We learned about two other very important governing equations of flow, Laplace equation and boundary layer equation. And since we have been learning about a lot of conservation equations, I think at this point, it's very important that you go through them once again, also keep track of the different assumptions we have made while deriving those equations. And that will help you to understand where each one of these equations apply. So it's a very important learning for all aerodynamicists or fluid dynamicists, where to apply what. Then in week 4, we went into airfoil geometry. That's a very important geometry in aerospace engineering. We looked at pressure distribution at an angle of attack. We learned about aerodynamic center of pressure, the different performance curves like CL alpha, CLCD, CM alpha, their significance. We understood flow separation and stall and how it reflects on these different curves. We learned about the influence of high lift devices, multi-element airfoils. How does it influence the performance of airfoil or further a finite wing? We learned about laminar and turbulent flow over an airfoil, as well as trailing edge noise, which is produced at the trailing tip of wing or airfoil. As regards the airfoil geometry, we went into the details like chord line, camber line, thickness distribution, leading edge, trailing edge, pressure distribution on airfoil. And then we moved into airfoil nomenclature. We learned about symmetric and cambered airfoils, forces and moments which act on them, aerodynamic center, center of pressure, etc. Then we learned about elementary flows, which are part and parcel of potential flow, like doublet, point vortex, vortex sheet, and then lifting and non-lifting flow. We learned about Kutta-Joukowski's theorem in that context, how to calculate the lift per unit span. We learned about the Kutta condition, which applies at the trailing edge of an airfoil. We learned about the Kelvin circulation theorem, how time rate of circulation on an airfoil is to be worked out or defined. We learned about the thin airfoil theory and the performance of a thin airfoil, both for symmetric and cambered airfoils. And then we finally learned about flow separation and stall dependence on airfoil shape. And we further learned about streamlined and block bodies. So there was a lot of learning from an applied angle this week. We then moved on to finite wing geometry after having studied about airfoil. And then we distinguished between an airfoil and finite wing. We talked about delta wing as well as its high angle of attack performance. We also talked about unsteady effects in airfoils and wings. We learned a little bit about what happens when a wing is pitching, heaving, flapping, etc. And briefly mentioned about a very interesting concept of dynamic stall. So flow features around a finite wing, how is it different from an airfoil? Formation of wingtip vortices in a finite aspect ratio wing, downwash, geometric angle of attack, induced angle of attack, effective angle of attack. These are the important things we learned. Different types of drag, including skin friction drag, pressure drag, profile drag, wave drag. These were learned. And in the context of the finite wing theory, we learned about the very important Biot-Savart law and the concept of vortex filaments. Then the Prandtl's lifting line theory, horseshoe vortex, bound and trailing vortex, etc., which are part and parcel of the finite wing theory modeling. We learned about elliptic and general lift distribution, aspect ratio of a finite wing, sweep in finite wings, tapering, and further induced drag factor and its variation with taper ratio. In the beginning, today we talked about one such problem which one of the students had pointed out. And so you may be recalling that there was a taper ratio that was defined. There was a certain aspect ratio that was defined when we solved that problem. So these are important terms, important identities in the finite wing theory. Then we learned about vortex roll-up and vortex-induced lift, especially in the context of delta wings, how they perform at high angle of attack, what is meant by vortex breakdown at high angle of attack. And then finally, we discussed a little bit about unsteady aerodynamic effects, like the way it happens in flapping wings of birds, as well as man-made flappers, like we see in micro-air vehicles and so on. Again, a lot of learning from the finite wing perspective, all the way comparing it with the infinite wings performance. And then we came into some more equations and some more flow regimes, more on the high speed side. We first learned about the full potential equation and its application. We learned that it is from the small perturbation equation perspective that we design such equations. And then we learn about shock and expansion wave theory, supersonic flow past a flat plate, flow through a CD nozzle, transonic and supersonic flow past an airfoil, shockwave boundary layer interaction, shock tube, and preliminary concepts of hypersonic flow. So this week was spent entirely on dealing with different kinds of equations, different kinds of concepts, flows in the high-speed regime. So we started by revising the thermodynamics principles, how they are important in compressible flows or high-speed flows. We discussed about it. We learned about first and second law. Rather, we kind of recapitulated. We learned about speed of sound and Mach number, weak and strong pressure waves like Mach waves and shock waves. Then we learned about velocity potential equation and its application in small perturbation problems where the source of the perturbation is very weak. We learned about concept of characteristics, which is so very important in compressible flows, where the flows essentially have hyperbolic nature. We learned about finite compression waves comprising of shocks and expansion waves, conservation equations applied to normal shock, oblique shock. In the context of oblique shock, we learned about theta beta M relation. And then we learned about Prandtl-Meyer expansion fan. We applied the shock expansion theory to solve problems on, say, an inclined flat plate. We then learned about quasi one-dimensional flow through a CD nozzle under different back pressures, under expanded, overexpanded flow, the very important area velocity relation, the concept of choking at the throat of the nozzle, characteristic Mach number. And then we also took up the airfoil problem and we studied the flow over a range of free stream Mach numbers. We looked at the concept of drag divergence Mach number, and then we moved on to shock tube and still further higher speed flows, which we call as the hypersonic flows, and the heated thin shock layers, which might occur in hypersonic flows. Incidentally, I'm offering a separate course on supersonic and hypersonic flows this semester. So this is being offered for the first time in this semester, and probably in foreseeable future, we may have a rerun, so you can have a look at that course too for further details on those heat regimes. In week 7 and 8, we looked at some issues, some computational issues related to aerodynamics, computing aerodynamic flows, the main steps and resources, panel and vortex lattice methods, Euler and Navier-Stokes equations, the first part. So we choose suitable mathematical models for computational modeling based on the flow physics that we are trying to capture. And for solving flow past an airfoil, whether we should use thin airfoil theory or potential flow or Euler equation or Navier-Stokes equation, this was the question we raised. We tried to answer what are the assumptions, approximations that are made in each model, which aspects of the flow can be modeled and predicted well using a particular governing equation or a system of governing equations. Then we talked about flow past individual aircraft components and complete aircraft or spacecraft. And then we looked at the different steps in computing, for example, pre-processing step, solver step, post-processing step, and so on. And we also discussed in detail an implicit technique, which is more appropriately, it's based on potential flow, modeling potential flow past bodies by solving Laplace equation, by using source panel and vortex panel methods for non-lifting and lifting flows, and then vortex lattice method for finite wings. So these are based on potential flow models. And then we moved on to the next week where we had the second part of Euler and Navier-Stokes equation simulations. What information can be extracted from numerical solutions, applications of computational aerodynamics, a few examples, and so on. So these were very much talking about both conceptual or theoretical issues as well as applications. We learned about mathematical classification of PDEs. A few minutes back, I was talking about hyperbolic equations. So this is where we learned how to classify equations, and PDEs can typically be classified into 3 categories: elliptic, parabolic, and hyperbolic, where each of the categories fit in the context of aerodynamics or fluid dynamics flows is what we discussed. We talked about real and imaginary characteristics, initial and boundary conditions, equilibrium and marching problems, the pre-processing step in the form of grid generation, grid index, and the solver step where we can have finite difference discretization, finite volume discretization, and so on. We stressed more on the finite difference scheme. We talked about explicit and implicit formulation, accuracy, stability, the CFL condition and its significance, dissipative and dispersive error, discretizing linear PDEs, and then moving on to 1D Euler equations, the flux vector form, certain other concepts related to Euler equations, how we deploy them to capture shocks. And then we moved on to the viscous form of the equations, 2D compressible Navier-Stokes equations. And then we talked about a very popular predictor-corrector time marching solution of laminar flow past a flat plate with leading edge weak shock during boundary layer displacement effect in a compressible boundary layer. So these are the things we tried to address in this week. Moving on to week 9, 9 to 12, we were concentrating on experimental aspects of aerodynamics. So in 9, we talked about experimental tools in aerodynamics, which are the wind tunnels, types of them, and design basics, similarity analysis, scaling, safety issues. So this is very much applied aerodynamics. We talked about the definition of wind tunnel, different kinds of tunnels, especially open and closed circuit tunnels, or low speed, high speed tunnels, and so on. We looked at the concept of jet power. We talked about component and section losses, loss coefficients, test section dynamic pressure, energy ratio, and then how to calculate the power input to the wind tunnel from axial fan if it is running the tunnel, optimum running condition for the fan. Then we went to the supersonic wind tunnel domain and did a little bit of study on that too. We talked about the possibility of having two throats, how to size the second throat with respect to the first one, whether it should be smaller or larger, why it should be that way. Again, we talked about continuous closed return supersonic wind tunnel. How do we compute power requirements there? And then we moved on to the similarity analysis. We introduced the Buckingham Pi theorem for dimensional analysis in experiments, the types of similarity which may exist, geometric, kinematic, dynamic, and so on. And finally, the safety issues while handling wind tunnels. So this week was entirely dedicated to study of wind tunnels. Week 10, which you are probably going through currently, is dealing with flow visualization techniques, model design and fabrication, model positioning, measurement with mechanical sensors, pitot-static tubes, pressure ports, mechanical balances, and so on. So flow visualization can be based on tracer-based methods or density-based methods. Surface flow visualization can happen through oil flow, tuft flow, free surface water flow, through hydraulic analogy. Flow field visualization can happen through smoke, dye. Optical techniques for high-speed flows are slightly different. They have to be in the form of either Schlieren or shadow graph. And that is where we try to look at the density gradients in the flow to visualize the flow. We looked at how model drawings or model specifications are made for fabrication, how we mount models, and then how do we make pressure measurement using mechanical devices, and how is it done in low speed as well as supersonic flows? What are the different devices that are used? For drag measurement, how do we do it? Is it only through direct weighing, or we can do it through wake survey? Whether we can do with a mechanical balance, what are the issues in using such a balance, and so on. So this was more on mechanical instrumentation for wind tunnels. And then we moved into electronic instrumentation, including electronic transducers, pressure gauges, strain gauge-based balancers, data acquisition systems and software, and also a little bit on measurement uncertainty. We looked at different types of electronic transducers, like variable resistance transducer. We learned about gauge factor, the different materials for transducer, how they are applied in Wheatstone bridge arrangement in the form of summing and differencing circuits, how they are more appropriate for either the moment or force measurements, while we apply it in strain gauge-based balances. We learned about electronic pressure sensor, scanner, and different kinds like absolute, gauge, or differential sensors, components of a data acquisition system like transducer, multiplexer, signal conditioner, AD converter, data card, acquisition and post-processing and analysis softwares, and so on. So this week was spent on electronic instrumentation for wind tunnel measurements. We also learned a little bit about error and uncertainty. And then the final week was spent on velocity measurement using particle image velocity velocimetry, which is one of the state-of-the-art techniques for uh, non-intrusive diagnostics of the flow, where we do not put in physically any kind of a probe into the flow, which to some extent disturbs the flow. But we have practically non-intrusive measurement of the flow. We can get the velocity vectors within the flow, and that gives a very good idea about the nature of the flow. How wind tunnel and associated instrumentation are used for performing aerodynamic studies, a few examples, and quick revision of the course content, which we are also doing now in the form of the live session 2. So obtaining the coherent flow structures in the flow through a non-intrusive method, that's the intention of particle image velocimetry. It's a laser-based technique. And we look at the entire flow field. We do not make point measurements. Optical access is necessary for performing this. We have to float very small tracer particles into the flow, which are practically non-intrusive in nature, and they should be capable of scattering the light that is incident, often a laser sheet. And then we try to figure out the velocity vectors in the flow field by tracking these particles. And we talk about the light sheet optics, suitable cameras, spatial cross-correlation analysis in order to obtain the velocity vectors from the instantaneous pictures of the flow field where the tracer particles are illuminated and they are translating through the field, and therefore they are getting displaced over short time intervals. Looking at the importance of a synchronizer in that setup. And then we looked at some of the experimental results on a flapping wing and load cell setup descriptions, which we made during that time. We talked about low speed wind tunnel calibration, when the fan is being run at different speeds, and how we have to calibrate the tunnel in terms of flow angularity, axial pressure gradient, turbulence intensity, pressure, and pressure distribution on a cylinder using pitot tube and manometer was explained. Forces on a wing using electronic balance and pressure measurement using scanner was explained. Different methods of obtaining test section Mach number of an intermittent blowdown supersonic wind tunnel was discussed. So we have tried covering a lot of application aspects also in this week. So if you go back to the different weeks, lecture contents, materials, then you will see there's a lot of material covered under the course. So if you are intending to appear for the final examination, then you should be thoroughly revising all the content, giving adequate weightage to each and every week. Do not be selective in studying. And if you devote enough time to the course contents, and if you have done your assignments well, and you are revising all that content regularly, then I'm sure you should be able to do very well in the exam. So I hope those who are going to appear for the exams will be doing very well. I wish all of them very good luck for the exam. And for the rest of the participants, I thank you once again for very effectively participating in the course. And I'm sure all of you are enjoying the course and finding it useful. So since we do not have much questions posted to the best of my knowledge, I think it is good time to close the live session 2. And today we tried addressing some of the queries which we have found in the Google forum. Additionally, we did a quick recapitulation of the course contents. So with this, I would like to close the live session 2. Thank you once again.
Thank you, sir.